Nearly 3 billion miles from the Sun, in the coldest, dimmest region of our solar system that still counts as a planet, something is happening to the sky above Pluto that shouldn't make physical sense. The very haze that blankets its atmosphere is somehow doing two contradictory things at once, soaking up what little sunlight ever reaches that far, and using that same absorbed energy to make the entire atmosphere colder, not warmer. For nearly a decade, one scientist argued that was exactly what was happening up there. And for nearly a decade, nobody had an instrument capable of proving him right. Then, in 2025, a set of new observations finally confirmed it using a telescope that had to solve a problem no observatory before it had ever managed to solve, separating Pluto's faint light from that of its own moon, close enough together in the sky that every telescope for the last 30 years had only ever seen them as a single blurred smear of infrared glow. This is the story of what the James Webb Space Telescope found when it finally turned its instruments toward Pluto. Why the answer took 8 years to confirm after it was first proposed, and why the strange, counterintuitive haze sitting in Pluto's sky right now might be quietly telling scientists something about the very early history of our own planet's atmosphere. To understand why this observation mattered so much, you have to start with a prediction made in 2017, years before Webb ever launched, by a planetary scientist who was confident he already knew what Webb would eventually find, if it ever got the chance to look. In 2017, Xi Zhang, a planetary scientist at the University of California, Santa Cruz, published a paper proposing something that ran directly against the conventional way scientists usually think about a planet's atmosphere. In most atmospheres, including Earth's, gases themselves are primarily responsible for regulating temperature, absorbing and releasing energy in ways that shape weather and climate over time. Zhang's paper proposed that Pluto's atmosphere worked differently. He suggested that tiny organic particles suspended high in Pluto's sky, a haze formed from sunlight-driven chemical reactions between methane and nitrogen, were doing something gases alone couldn't do on their own. During Pluto's brief daytime, these haze particles would absorb solar energy. Then, once night fell, rather than holding onto that energy the way a planet's surface typically does, the particles would radiate it away extremely efficiently as infrared heat, losing energy faster than they gained it. The net effect, if Zhang was right, would be an atmosphere that actually cooled itself down specifically because of the haze absorbing sunlight, not despite it. It was, by his own admission, an unusual idea for the field, since it meant the classic assumption that gases alone control a planet's atmospheric temperature simply didn't apply to a world like Pluto. There was a very specific, testable prediction buried inside that theory. If Zhang was correct, the haze itself should be emitting a detectable amount of mid-infrared radiation, a very particular wavelength of light produced specifically by particles losing heat this efficiently. The problem was that no telescope in 1997, 2004, or 2012, when European and American infrared observatories first picked up faint traces of mid-infrared emission coming from the general direction of the Pluto system, had ever been sensitive enough or precise enough to actually separate that emission cleanly, to determine definitively whether it was coming from Pluto's haze, from Pluto's icy surface, or from its large moon Charon, orbiting close enough beside it that from Earth's perspective, and from every telescope operating at the time, the two worlds simply blurred together into a single point of light. Zhang's prediction sat there, plausible but unconfirmed, for years, waiting for an instrument capable of resolving that ambiguity. That instrument turned out to be the James Webb Space Telescope, and specifically its mid-infrared instrument known as MIRI, one of 4 primary science instruments carried aboard the observatory since its launch on Christmas Day 2021. Here's why Webb succeeded where every previous mission had come up short. Webb's primary mirror spans 21 feet across, roughly 2.5 times the diameter of the Hubble Space Telescope's mirror, and considerably larger than any of the earlier infrared observatories that had glimpsed the faint mid-infrared glow of the Pluto system decades earlier. That larger mirror, combined with MIRI's extraordinary sensitivity across a wavelength range of roughly 5 to 28 micrometers, finally gave astronomers enough resolving power to do something no previous telescope had managed: cleanly separate Pluto's thermal glow from Charon's, and measure the mid-infrared emission coming from each world independently, rather than as a single blurred signal. In 2022, mission scientists pointed Webb toward the Pluto-Charon system and captured a set of observations over roughly a week, watching how the thermal signal from each body changed as the two worlds rotated. What they found, once the analysis was completed and published in the journal Nature Astronomy in June of 2025, confirmed almost exactly what Zhang had proposed 8 years earlier. "This is unique in the solar system," said Tanguy Bertrand, an astronomer at the Paris Observatory who led the analysis, in comments reported by Live Science and Space, calm following the publication. "It's a new kind of climate, let's say." Webb's data showed that Pluto's high-altitude haze really was acting as the primary driver of the dwarf planet's atmospheric energy balance, absorbing incoming solar ultraviolet radiation during the day and radiating a strong, clearly measurable mid-infrared signature at night, exactly the signature Zhang's model had predicted nearly a decade earlier. We were really proud, because it confirmed our prediction, Zhang said, in comments reported by his own university's news office. In planetary science, it's not common to have a hypothesis confirmed so quickly, within just a few years, so we feel pretty lucky and very excited. It's worth pausing on that quote, because it's an honest, refreshingly modest description of how genuine scientific progress actually happens, methodically, over years, rather than through some sudden dramatic reveal. But confirming that the haze cools the atmosphere was only half of what Webb's data revealed, and the second half is, in some ways, the more genuinely strange finding, because it describes the same haze doing something that sounds directly contradictory to the cooling effect just described. According to the same body of research, Pluto's high-altitude haze isn't simply cooling the atmosphere, it's simultaneously helping strip that same atmosphere away, particle by particle, out into space. Data gathered years earlier by NASA's New Horizons spacecraft, which conducted the only close flyby of Pluto in history on July 14, 2015, had already established that Pluto's atmosphere leaks methane into space at a measurable, steady rate, estimated at nearly 3 pounds of material escaping every single second. What Webb's newer observations helped clarify was the actual physical mechanism behind that ongoing loss. According to Bertrand and his colleagues, extreme ultraviolet radiation from the distant sun gets absorbed by that same high-altitude haze, and in the process, heats individual particles enough that they gain sufficient energy to escape Pluto's famously weak gravitational pull entirely, carrying trace amounts of methane and other volatile compounds away from the planet permanently. A significant fraction of the incoming solar extreme ultraviolet radiation is absorbed by the upper atmosphere, leading to heating that powers atmospheric mass loss, Bertrand explained, according to Space.com's coverage of the findings. Atmospheric gases such as nitrogen and methane are responsible for absorbing radiation at these wavelengths. Put those two findings together, and you get something that initially sounds like a contradiction but isn't, once you understand the physics involved. The same haze is simultaneously cooling Pluto's broader atmosphere by radiating heat away efficiently at night, while also using absorbed solar energy to actively energize and eject a small but steady stream of particles out into space entirely. It's not two competing processes fighting against each other. It's one unified system, doing two different jobs with the same underlying mechanism, something researchers describe as playing a key role in the dwarf planet's overall energy balance. There's a third piece to this story that involves Pluto's largest moon, Charon, and a strange, almost intimate kind of interaction between the two worlds that Webb's observations helped bring into sharper focus. Unlike Pluto, Charon has essentially no atmosphere of its own to speak of, and Webb's data confirmed that its surface is comparatively uniform, dominated largely by water ice mixed with ammonia-based compounds, without the complex chemically active haze that dominates Pluto's sky. But Charon isn't entirely untouched by its neighbor's atmosphere. Its polar regions carry a distinctive reddish hue, and that coloring turns out to come directly from Pluto itself. As methane molecules escape Pluto's atmosphere and drift outward into space, roughly 2.5% of that escaping material ends up captured by Charon's gravity instead, striking its polar surfaces and undergoing chemical transformation through prolonged exposure to sunlight and radiation, gradually building up the same kind of reddish organic compounds called tholins that give Pluto's own surface its famous reddish-brown coloring. In effect, Pluto is slowly painting parts of its own moon, one escaping methane molecule at a time, a planetary scale interaction unlike anything else documented anywhere in our solar system. It's worth being precise here about exactly what Webb accomplished technically, because the achievement itself is a meaningful part of the story, separate from what the data actually revealed about Pluto's climate. Mid-infrared emission from the general direction of the Pluto-Charon system had actually been detected before Webb ever launched, first by the European Infrared Space Observatory back in 1997, then by NASA's Spitzer Space Telescope in 2004, and again by the European Herschel Space Observatory in 2012. Each of those earlier detections confirmed that something in that part of the sky was glowing faintly in mid-infrared light, but none of them had the resolving power to determine with any confidence whether that glow was coming from Pluto's haze, from its icy surface, or from Charon itself. From Earth's perspective, at a distance of roughly 3 billion miles, Pluto and Charon sit close enough together that older telescopes simply couldn't tell them apart in this particular wavelength range. Webb's 2022 observations were the first in history to cleanly separate the two, measuring distinct thermal emission from Pluto and from Charon independently at 4 specific mid-infrared wavelengths, 15, 18, 21, and 25 micrometers. That capability alone, resolving two close, faint objects billions of miles away into two independently measurable thermal sources, represents a genuine technical milestone, one that simply wasn't achievable with any instrument that came before it. There's a reasonable question worth addressing directly here, given how this story is often framed in more sensational retellings. Is any of this actually surprising in the sense of defying known physics, or is it simply new and previously unconfirmed? The honest answer is the second one, and it's worth being clear about that distinction rather than blurring it for effect. Nothing about Pluto's haze behavior violates any law of physics. The underlying photochemistry, sunlight driving chemical reactions and a mix of methane and nitrogen to produce organic haze particles, is a well-understood process, one that's been studied for decades on Saturn's moon Titan, which has a thick, hazy atmosphere built from very similar chemistry. What made the Pluto findings genuinely noteworthy wasn't that they broke any existing rule of atmospheric science. It's that they revealed an atmosphere behaving according to a mechanism nobody had previously confirmed operating as the dominant climate driver on any world in our solar system, a haze functioning less like a passive layer of particles and more like the atmosphere's primary thermostat, something Bertrand and his colleagues describe directly and without exaggeration as a genuinely new kind of climate. That distinction matters for a second reason too, one that connects this distant frozen dwarf planet directly back to our own. Researchers involved in the study have pointed out that studying how Pluto's haze regulates its atmosphere and drives the slow, steady loss of gas into space may offer real useful insight into a much bigger question: how Earth's own atmosphere evolved from its earliest, most primitive chemical state, likely dominated by nitrogen and simple hydrocarbons, not unlike the chemistry currently playing out in Pluto's sky, into the oxygen-rich, life-supporting atmosphere we depend on today. That's a genuinely compelling scientific through-line, one that doesn't require any exaggeration or embellishment to justify the attention this research has received. A haze forming on a small, frozen world nearly 40 times farther from the Sun than Earth is maybe running a simplified version of atmospheric chemistry relevant to understanding our own planet's deep past. A natural laboratory sitting nearly 3 billion miles away doing an experiment nobody had to build or fund, one that's simply been running quietly since long before humans existed to study it. It's also worth putting these new findings in proper context, alongside what we already knew about Pluto before Webb ever turned its instruments in that direction, because it helps illustrate just how much groundwork had already been laid by an earlier, very different kind of mission. On July 14th, 2015, NASA's New Horizons spacecraft became the first, and remains to this day the only, spacecraft to fly directly past Pluto, passing within about 1,800 miles of its surface after a journey of more than 9 years across the solar system. That flyby fundamentally transformed scientific understanding of Pluto almost overnight, revealing a world that was anything but the frozen, geologically dead relic many scientists had expected. New Horizons photographed vast plains of nitrogen ice, mountain ranges built from water ice rigid enough to hold their shape at temperatures hundreds of degrees below zero, and a striking, bright, heart-shaped basin now known as Sputnik Planitia, evidence of ongoing geological activity on a world previously assumed to have gone cold and still billions of years ago. The spacecraft also directly imaged Pluto's atmospheric haze for the first time, capturing a delicate blue atmospheric shell extending more than 125 miles above the surface, structured into at least 20 distinct layers, a level of complexity nobody had anticipated finding around such a small, distant world. It was New Horizons' direct measurements of methane escaping from that atmosphere that first established the roughly 3 pounds per second rate of atmospheric loss that Webb's more recent observations helped explain the underlying mechanism behind. Understanding how those two missions fit together says something important about how planetary science actually progresses, in careful, sequential steps rather than through any single dramatic revelation. New Horizons gave scientists an extraordinarily detailed close-up snapshot of Pluto's surface and atmosphere, but only for the brief window of its flyby, a matter of hours as it sped past at more than 30,000 miles per hour, unable to linger and observe changes over time. Webb, positioned far closer to home in an orbit around a point in space roughly 1 million miles from Earth, can't match that resolution of surface detail, but it can do something New Horizons never could. Observe the Pluto-Charon system repeatedly over extended periods, watching how conditions actually change across Pluto's long, slow rotation and its extraordinarily lengthy 248-year orbit around the Sun. The two missions complement each other almost perfectly, one providing a single, richly detailed close-up, the other providing sustained, repeatable monitoring from a distance, and together they've produced a far more complete picture of Pluto's atmosphere than either could have generated alone. None of this required exaggeration to be worth paying attention to. A small, icy world sitting nearly 3 billion miles from the Sun, once assumed to be a simple, frozen, geologically inert leftover from the solar system's formation, turns out to be running an atmospheric climate system unlike anything else documented anywhere else among the planets. One where a layer of organic haze particles functions as the primary regulator of atmospheric temperature, simultaneously cooling the broader atmosphere while actively powering its own slow, steady escape into space. That finding took nearly a decade to move from theoretical prediction to confirmed observation, not because anyone was hiding anything or because the science was uncertain in some dramatic sense, but because building an instrument sensitive and precise enough to actually test the prediction took exactly that long. Requiring a telescope with a mirror over 20 feet across, orbiting nearly 1,000,000 miles from Earth, specifically engineered to see faint, cold, distant objects with a level of clarity no previous observatory had ever achieved. There's still more work ahead for researchers studying the system. Bertrand and his colleagues have noted that similar haze-driven climate dynamics may be at play on other haze-shrouded worlds throughout the solar system and beyond. Including some of the hazy exoplanets astronomers have begun cataloging in increasing numbers over the past several years. Confirming whether Pluto's haze-driven climate represents a rare exception or a more common pattern across other cold, distant worlds will require additional observations, comparing Pluto's atmospheric behavior against other icy bodies in the outer solar system, and eventually against atmospheres detected on planets orbiting other stars entirely. That work is already underway, using the same instrument and the same careful, patient approach that took 8 years to confirm what one scientist first proposed back in 2017, based on nothing more than a hunch about how a small world at the edge of our solar system might be quietly rewriting the rules of atmospheric science, one absorbed photon at a time. Nearly 3 billion miles from where you're sitting right now, that haze is still there, doing exactly what Webb confirmed it does, absorbing what little sunlight ever reaches that far, cooling an entire planet's atmosphere in the process, and steadily, patiently carrying pieces of that same atmosphere away into space, one escaping molecule at a time, in a process that's been running quietly since long before any human telescope was ever built to notice it. If you want to see what scientists find next as they keep watching this distant, quietly strange little world, that story is still actively being written. Subscribe if you'd like to follow where it goes.